In the name of Allah, the most beneficent and merciful. Assalamu alaikum, dear girls. I am Sada Fishwak, and today we are going to do the exercise which we started in the previous lecture, that is chapter 11, Electrostatics. And in the previous lecture, we discussed multiple choice questions of the exercise and some conceptual questions. After listening to today's lecture, you would be able to understand all the conceptual questions of the exercise, and we are going to do numerical problems. Okay, first of all, we come to conceptual questions. Question number 9, we have to start from this question. Can different equipotential lines cross each other? Explain. In order to answer this question, you must be knowing the concept of equipotential lines. If you remember the topic, the article I taught you in this figure, this is a unit positive charge, and the lines, electric lines of force are moving radially outward, and these dotted circles shows equipotential lines. And at every point on the dotted portion shows equal distance, so the work done is the same. But here we have to answer that can different electric lines cross each other? The answer is no. If equipotential lines intersect, then their corresponding electric lines are also intersect, which is not possible. So you can see here, these are different equipotential lines. And no two lines are intersecting each other because the distance of consecutive lines is the same. And when these two lines are intersecting each other, it means their interdistance change. It means at a single point, there are two directions, because I told you in the second lecture, I think, that when you represent lines of force, then the lines of force, the curved lines of force, at every point, the direction of the field is represented by drawing the tangent. And at one point, only the one direction of the field lines is given. If there are two lines crossing each other, it means at a single point there are two different directions. The field is giving you the two different directions, which is physically not possible. Otherwise, electric field will have more than one direction at a point which is not possible. Question number 10. Water has a large dielectric constant, but it is rarely used in capacitors. Explain why. If you remember the previous topic, capacitors, I told you that capacity of a parallel plate capacitor could be increased by introducing a dielectric. And what is a dielectric? Dielectric, it may be an insulator, any insulator. It may be mica, it may be glass, it may be rubber, whatever. So here the question is that why don't we take water as a dielectric constant? Pure water is a non-polar dielectric. I told you about non-polar dielectrics. These are the insulators which have no poles. I told you the polarization of dielectric, how the atoms of dielectric, they are converted into poles. One end negative, other end positive, right? Like this, pure water is also a non-polar dielectric. It means that in the presence of battery, in the presence of electric current, it makes the poles. Water molecules are moving randomly, but we all know water as compared to solid. The water molecules, they move randomly. Their degree of motion is more as compared to solids. They are not tightly bound to each other. In an electric field, the water molecules are polarized. Okay, let's see. If we are taking water as a dielectric, and we insert it in the circuit diagram where there is a battery, then what will happen after passing the current from the battery? So what will happen? The water molecules would be polarized because it is a non-polar, but they are not at rest. But as we all know that the molecules of water is at the state of random motion, so they are not at rest and cannot induce charges to produce electric field like solid dielectric. The motion of water molecules varies the capacity of a capacitor continuously, because continuously the molecules or the atoms of water are moving randomly. That's why we are unable to keep its motion constant, and the capacity of a capacitor definitely it would change. Therefore water cannot be used as a dielectric in a capacitor. Water can produce corrosion to plates. Corrosion means damage. It may damage the plates of a parallel plate capacitor. And secondly, it can ionize the plates or any salts within the capacitor. So that is the cause of corrosion in dielectrics in capacitors. Question number 11. A capacitor is connected in series with a resistor and charge. Let me see here a circuit diagram. Here is a resistor of resistance R. Here is a capacitor of capacitance C, and it is connected in series. Explain why the potential difference across the resistor decreases with the time during the charging. For an RC circuit connected with a battery source, according to conservation of energy. What do you mean by conservation of energy? Energy in the total system, it remains constant. The source voltage must be equal to voltage drop across the capacitor and voltage drop across the resistor. According to law of conservation of energy, when the switch is closed, AB terminals are connected, then the circuit is ready, and in that case current flows, and when the charges they reach the resistor, then there would be a drop in potential, and also when it reaches the capacitor, again there is a drop in potential or the voltage, but this happens all according to law of conservation of energy. As the charge stored Q will increase the voltage across capacitor, that is Vc is equal to Q over C, where what is Vc? Vc is giving you girls the voltage or the potential drop across the plates of the capacitor, that is given by Vc, it is equal to Q over C, where what is Q? Q is the charge which is stored at the plates of the capacitor, and C is the capacitance of this capacitor which is connected in series with R. So results Vc, it increases, so V into R, where what is V into R? That is V into R is V is giving you the voltage and R is giving you the resistance. It will decrease in order to conserve the energy in series combination. Otherwise what will happen? There would be a decrease in energy due to two potential drops across R and C, which would be violation of law of conservation of energy. Question number 12. Sketch the graphs of potential difference against time for A part, a discharging capacitor, B, a charging capacitor. First of all, we come to charging capacitor, and the circuit diagram, that is again an RC series circuit, switch and the battery. When switch S is connected with terminals A, when A and B are connected, it means now the circuit is completed. The capacitor will start to store charge. The value of charge Q in any instant of time t in terms of equilibrium value of Q, that is Q naught, can be expressed as Q is equal to Q naught. So at RC is equal to T, I told you in the previous topic, that is RC is giving you the time constant, and during that time constant, when the charging process starts, the maximum charge is stored at the plates of the capacitor, given by this relation Q is equal to Q naught into 1 minus E minus T over RC. So increase in charge with time T is exponential, that is Q is equal to, putting this Q is equal to CV. When we put here Q is equal to CV, what happens? That is given by CV. When we put Q naught is equal to CV naught over here, so CC cancels on both sides, and what it results? It results So as we all know that for the capacitor, Q is directly proportional to V, that is the potential difference. And when we rewrite the same relation for equilibrium, when Q naught is deposited at the plates of the capacitor, then we rewrite the equation as Q naught is equal to C into V naught. By using these two values of Q and Q naught here in this equation, what happens? CC cancels on both sides, and what we get here V is equal to V naught into 1 minus exponent minus T over RC. And when we draw a graph voltage versus time, then this curve comes for the charging of a capacitor. In case of discharging of capacitor, what happens? When the switch S is connected with terminal B, the capacitor will start to discharge. The charge Q at any instant of time t in terms of equilibrium values can be expressed as Q is equal to Q naught E minus 1 over RC, decreases exponentially with time, as we all know that Q is proportional to V. So again, by using the values of Q, that is CV, Q naught, that is CV naught, CC cancel on both sides, and just is in the same way as previously for the charging process. In case of discharging process, we get the relation V is equal to V naught E minus T over RC, and graphically that could be drawn by plotting a graph voltage versus time, and we have to start the graph from the maximum value of charge, that is Q naught, and in this way the energy is utilized. All right, now we come to question number 13. Compare the formula for capacitors in series and parallel with those for resistors in series and parallel. Explain why the pattern is different. All right, we notice over here that when we take 3 resistors, in case of combination of resistors in series and parallel, in case of combination of capacitors in series and parallel, what happens? We are going to discuss it mathematically. Let me consider first the resistors in series R1, R2, R3. These are 3 resistors, and these are connected in series combination, and we all know for the series combination, because the path of the current is the same, that's why I1 passing through R1, I2 passing through R2, I3 passing through R3, it is same. So instead of writing 1s, 2s and 3s, we just write down here I. All right. And we notice one thing, that if this terminal of R1 is connected with the terminal of the battery, then we notice that if this is the positive terminal of the battery, so here is positive, negative, positive, negative, and vice versa. We notice that different terminals of resistors are connected with positive as well as negative terminals of the battery. So it means there is a change in the potential difference. All the terminals of the resistors are not connected with the same terminal of the battery. That's why in that case V1, that is the voltage drop across R1, is not equal to V2, it is not equal to V3. Okay, from Ohm's law we all know that V is equal to IR, and for V, that is V is given by the voltage, that is the power supply coming from the battery, that is V is equal to V1 the voltage drop across R1 plus V2 plus V3. We write down this equation. From Ohm's law, we all know V is equal to IR. So what would be V1? V1 would be equal to I into R1. What would be V2? It would be equal to I into R2. And what would be V3? It would be equal to I into R3. So using all these values in this equation, we get here, and in this step what we do, we take I as common. What would be left inside? R1 plus R2 plus R3. So we write down I outside the bracket, and inside the bracket we are writing R1 plus R2 plus R3. So this I cancels with this I, and what is left here? R is equal to R1 plus R2 plus R3. So equivalent resistance, what does it mean? How we read it? That this R, which is an equivalent resistance, is greater than each of the resistance, that is each of the individual resistance. So this was the series combination for the resistor. Now we come to series combination for the capacitor. Here are three capacitors, C1, C2, C3. These are connected in series combination, and we notice over here that the charges, because the path of the current is the same, so Q1 the charge at C1, Q2 charge at C2, Q3 charge at C3, it would be same. So instead of writing Q1, Q2, Q3, let me write it is all equal to Q. And we notice over here that when we connect C1 with the terminal of the battery, then definitely the other plate of C1 is connected with this plate of C2 and vice versa. We notice here that all the plates are connected with different points, so it has different values of V. So we write down here combined voltage, that is a voltage of the source V is equal to V1 plus V2 plus V3. Alright, so here we have to write down the equation of capacitor. We all know that Q is equal to C into V. So what would be V? V is equal to Q by C. Similarly, what would be V1? Q over C1, V2, Q over C2, V3, Q over C3. So again we have to take, because charge is the same. Alright, so we take Q common, and after taking common, Q cancels on both sides, and what is left behind? 1 over C is equal to 1 over C1 plus 1 over C2 plus 1 over C3. So we notice here that equivalent resistance is smaller than each individual resistance. So this is the way we have proved that when we make a comparison between these two combinations, then two different relations are coming up. For resistors series combinations, we get the equivalent resistance as, and for capacitors in series, we get the equivalent capacitance as given by this relation. Okay, now we come to the parallel combination. When R1, R2, R3, these are connected in parallel, then what happens? These are connected, it means all the terminals, that is, if we say positive, 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 these are all connected with the positive terminal of the battery, and all the negative, negative, negative terminals of R1, R2, R3, these are connected with the negative terminal of the battery. So carrying V1, V2, V3 equivalent. But in that case, because there are three paths for the current, so I1 is not equal to I2, is not equal to I3. So what we say that if the total current of the circuit is I, then it would be split into I1 plus I2 plus I3. We write down this equation. From Ohm's law, we know that V is equal to IR. So what would be I from Ohm's law? Yes, it would be V by R. What would be I1? V over R1. I2 V over R2, I3 V over R3. So again we have to take this V common. So this V would be cancelled with this V. What would be left behind? 1 over R is equal to 1 over R1 plus 1 over R3 plus 1 over R3. So equivalent resistance is smaller than each individual resistance. Similarly, capacitor in parallel, C1, C2, C3, when these are connected in parallel, again I told you that voltage would be same, and also because the path of the current is different, definitely Q1, Q2, Q3 means different charges are deposited or stored at the plates of the capacitors. So it means Q1 is not equal to Q2 is not equal to Q3. So it means the total charge Q is equal to the sum of the individual charges deposited at different capacitors, that is Q is equal to Q1 plus Q2 plus Q3. So if, as we know, Q is equal to CV, Q1 would be CV1, Q2 is equal to CV2, Q3 is equal to CV3. Alright, taking C common, what would be left inside? C1 plus C2 plus C3, that is CC cancels over here, and what we get here in that case. So when we put the values of Q1, that is C1V, Q2, C2V, Q3, C3V in this equation, what we get by taking V common, so V cancel on both sides, and what we get here, C is equal to C1 plus C2 plus C3. So equivalent capacitance is greater than each. We notice one thing, that for resistors and capacitors, when these are connected in series and parallel, then the equations which come are different. Why? Because resistor, as we all know, is a device which resists the flow of current. Alright, and capacitor is a device which is used to store the charge. So that's why, due to this reason, we notice that different equations come for a parallel. We or notice that equivalent resistance is smaller than each, and in case of parallel combination for capacitor, equivalent capacitance is greater than each, and the same is the case in case of series combination. Alright, question number 14. Explain why capacitors are of little use for storage of energy from normal domestic purposes of lighting, heating, and so on. Capacitors are of little use of storage energy for normal domestic purposes due to following reasons. There is a limit of charge which can be stored on the plates of the capacitor during its charging. So as we all know that every capacitor has some capacity of storing charge. It depends upon its size. We are unable to store charge more than the capacity of any capacitor. As a charge capacitor is connected to a load, load means any device. For example, we are in case of capacitor fan, we are using a capacitor and the load is fan. This potential difference cannot remain constant across ends of a capacitor for a longer time. According to the equation, Q is equal to CV, where Q is directly proportional to V. So due to this reason, we are not using capacitors for normal and domestic purposes of lighting, heating, and so on. Now, girls, we come to numerical problems. The first numerical problem of the book in the exercise. What is magnitude of the force of attractions between an ion nucleus bearing charge Q is equal to 26e and its innermost electron if the distance between them is 1 into 10 to the power minus 12 meter? This is the statement of numerical number 1. Then we come to data given. In the data given, very clear that here we are talking about an atom that is having a nucleus and its innermost shell there is an electron. So we all know that what is the charge on this electron, that is Q1. Let me say it is Q1. And it is equal to 1.6 into 10 raised to the power minus 19 coulomb. And what is the charge of this nucleus bearing this charge? Q is equal to 26E, that is given by Q2, and Q2 is equal to 26 into E. If you remember the first lecture, I told you quantization of charge, Q is equal to N into E, where what was N? N was the number of charged particles, and here this equation is coming from that basic equation. So Q2 is equal to 26 into E. 26 are the number of particles, and what is E? E is the charge on the charged particle, that is the electron. So we are going to multiply 26 with the E, that is given by 41.6 into 10 raised to the power minus 19 coulomb. Okay, what is the separation between the two charges? Which two charges we are talking about? That is the nucleus and the electron. So what is the separation? 1 into 10 to the power minus 12 meter. All right. And what is this? We all know that is K, that is the Coulomb's constant. 9 into 10 to the power 9 Newton meter square over Coulomb square. It is always given. All right. And what we have to find? We have to find the magnitude of force of attraction. That is the electric force we have to find, and from where? Definitely this is the Coulomb force, because here we are dealing with the two charged particles, one electron and other is a nucleus. Okay. From Coulomb's law, we all know that F is equal to K Q1 Q2 over R square. All right. And by putting the values, as I told you about Q1 and Q2 and this is R square. So putting all these values, what we get? F is equal to 6 into 10 to the power minus 3 Newton. Okay. Dear students, you are going to solve it yourself. All right. Now we come to numerical number 2. Charges 2 microcoulomb, minus 3 microcoulomb and 4 microcoulomb are placed in air at the vertices of an equilateral triangles of sides 10 centimeter. What is the magnitude of resultant force acting on 4 microcoulomb charge? So you have to understand the situation. We are having three charges, 2 microcoulomb, minus 3 microcoulomb and 4 microcoulomb, where they are placed at the vertices of an equilateral triangle. We must be knowing about equilateral triangle. It's a triangle having 3 equal sides. So let me see here, this is an equilateral triangle, and at the vertices, these are the vertices of an equilateral triangle, and at the vertices there are 3 charges which are placed, that is Q1. Let me call the first one is Q1, this is Q2 and this is Q3. all right. So this is Q1 2 microcoulomb, this is Q2 minus 3 microcoulomb, this is a negatively charged particle, and this is the third one, that is 4 plus 4 microcoulomb. These are placed over here. all right. And at a distance of 10 centimeters. So what does it mean? Equilateral triangle means either it is Q1 Q2, the distance is 10 centimeter, either it is Q2 Q3, so the distance is again 10 centimeter, either it is Q1 Q3, the distance is the same as that of 10 centimeter. all right. So we have to find the magnitude of the resultant force which are acting on 4 microcoulomb. So this is 4 microcoulomb charge and it is represented by Q3. So we are going to find the magnitude of the resultant force which is acting on this Q3. So it means we have to find the force due to Q1, Q2 on Q3. So first of all we come to data given. The 3 charges, the magnitudes of the charges are given. Q1 is equal to 2 into 10 to the power minus 6 coulomb. Q2 is minus 3 microcoulomb. The value Q3 plus 4 microcoulomb plus 4 into 10 to the power minus 6 coulomb. We have to convert it into SI unit. all right. And what is the separation between the charges? Let me call it as R in the figure. So R is equal to 10 centimeter and we are going to convert it into meter, that is given by 0.1 meter. all right. So here, because we are talking about the charges and we are going to calculate the resultant force on these charges, so definitely what comes in your mind, we have to use the Coulomb's law, and when we are using Coulomb's law, then we come to the electric constant, that is K, which is equal to, it has a fixed numerical value, I told you earlier, and 9 into 10 raised to the power 9 Newton meter square over Coulomb square. What we have to find? We have to find F on 4 microcoulomb. Okay, now we come to the solution of the question. In this case, what we have to do, now the repulsive force on charge 4 microcoulomb due to Q1. Okay, what does it mean? We are talking about these two forces. Which one? Q1 and Q3. These are the force. These are the two charges which carry positive charge. That is Q1 plus this Q3, again it is plus. So the plus means there would be a force of repulsion. So the repulsive force is given by the magnitude 1 over 4 pi epsilon naught Q2 Q3 over R square. All right. Q1 Q3 over R square. Okay, so we have to use here the Coulomb's law equation between Q1 and Q3 charge, and by putting the value of K, then Q1, then Q3 over R square. When we put all the values, what we get here equation number 1. We call it as F1, which is equal to 7.2 Newton. All right. Similarly, the attractive force on 4 microcoulomb due to Q2. Why attractive? Because Q2 is a negative charge. So there would be a force of attraction. And from Coulomb's law, that force of attraction is given by F2. That is 1 over 4 pi epsilon naught Q2 Q3 over R square. Similarly, you are going to put the value for K, for Q2, for Q3 over R square. When we put all the values, what we get? F2 is equal to minus 10.8 Newton. Let me call this equation as equation number 2. Alright, where the negative sign shows that there is a force of attraction between the charges. Which one? Q2 and Q3. Alright, since the triangle is equilateral triangle, so each force F1 and F2 making angles theta 1 and theta 2 with the axis is 60 degrees. Now we come back to the figure and we notice over here that it is an equilateral triangle, and from mathematics we all know that for an equilateral triangle, all the three angles of an equilateral triangle is of measure 60 degrees. So when this is the force acting on this charge Q3, and if we represent this force graphically, this is the force, and if we resolve this force into components, so what happens? That is sine of 60, this vertical component, this is the horizontal component, and this is the direction of the horizontal component of force, right? This is the direction, and this is the direction of horizontal component, that is rightward, and this is the direction of vertical component, that is upward. All right. Now, when we come to this fact, the figure, and how you have resolved the forces F1 and F2 into its component, then what happens again, because you have to find the resultant force on Q3. So like the fact that here the force F1 is acting due to this, we have resolved F1 into its component. Just in the same way, we are going to resolve this second force due to this charge Q3 into its component. Which component? That is the vertical. From the head we drop a perpendicular. This is the reference line, and according to head to tail rule of vector addition, when you draw the arrowhead, so what does it mean? This if this is this was F1, so this is F2, so this is giving you F2 sine of 60. What would be the direction? Downward. So this is F2 cos of 60. What would be the direction? Rightward. All right. So in order to find the total force, you have to consider first all the horizontal components of forces, all the vertical component of the forces. So like here, Fx is equal to F1x plus F2x. All right, that means Fx is equal to, what is f1x? F1 cos of theta 1, f2x, f2 cos of theta 2. We all know that is theta 1, theta 2, that is 60 degrees. And what is the value of f1 and f2? We have calculated earlier. You are going to put the values. When we put all these values, do remember f2 is having a negative sign over here. So overall what we get, fx is equal to minus 1.8 Newton. So in this way, we will find the y component of the resultant force, that is given by Fy. It is equal to F1y plus F2y, alright, that is F1 sine theta 1 plus F2 sine theta 2. So by putting the value of theta 1, theta 2, F1, F2, finally what we get here? We get here equation number 4. So this is 15.6 Newton, because we have to find the magnitude of the resultant force, and as we know that F is equal to under root Fx square plus Fy square. By putting the value of Fx and Fy, what we get? We get here the resultant force given by 15.7 Newton. Okay, we come to numerical number 3. A charge Q is placed of the center of the line joining the two charges, each of magnitude q. Prove that the system of three charges will be in equilibrium if q is equal to minus q over 4. We are going to prove it. Okay, let me write down the data given first. Separation between the charge q and capital Q. So let me see here that there are two charges of equal magnitude, capital Q and capital Q. In the middle point, there is a charge small q which is placed in such a way that this q is lying in the middle of these two charges, and the distance of q with respect to this charge is r, with respect to this charge is again r. So what would be the distance between the two charges, capital Q's? That would be r plus r gives you 2r. Alright, so we write down here this fact in the data given. Separation between the charges q and q, the small q and capital Q, that is small r. Separation between the charges q and q, that is 2r. What we have to find? We have to prove that q is equal to minus q by 4. We are going to prove it. Now we come to the solution. From Coulomb's law, the system will be in equilibrium when F, that is the force on small q due to capital Q charge, plus force due to this charge capital Q on the other charge capital Q is equal to 0. So this is the way how we use this equation, because the system, it is given that the three charges will be in equilibrium if q is equal to minus q by 4. So if the two charges are in equilibrium, we are going to use this equation. So by Coulomb's law, put the value of the force on small q due to capital Q. It would be k small q capital Q over r square, alright, plus the force. We are applying here Coulomb's law again. So that would be k, the first charge q, the second charge capital Q again, and what is the distance? 2r whole square. Alright, here comes this equation. And what we are going to do here, we have taken k capital Q over r square common. What is left inside? Q plus q by 4 is equal to 0. So from mathematics, either this term is equal to 0 or this term which is written inside the bracket is equal to 0. Okay, when we put q plus q by 4 is equal to 0, what comes? The value of small q, which is equal to minus q by 4. Okay, we come to numerical number 4. In case of numerical number 4, two equal and opposite charges of magnitude 2 into 10 to the power minus 7 coulomb are placed 15 centimeter